Okay, in this video lesson, we're going to look at designing experiments for determining the 6 motor model parameters. This is going to be split into 2 lessons. The first one is going to talk more about the approach that we might take in determining the 6 parameters, while the second one will give the specifics of the experiments. I've broken this up because for some of you watching this, your assignment is to actually come up with these experiments. So I don't want to give all that away in this first video, but I want to give you some tips and point you in the right direction so that you can efficiently arrive at those experiments. And then subsequently to determining those yourselves, you can check the second video to compare your experiments with what I have suggested. There are multiple ways to arrive at these 6 parameters, so by no means is what I'm presenting the only way to do it. There may be better ways to do it, but I have listed here the objectives, and some of these objectives are going to motivate how we're going to, or why I end up with the experiments that I will eventually propose. Okay, so the objective is to determine, first objective is to determine all 6 parameters empirically using common electronic lab equipment. Things such as a digital multimeter, digital storage oscilloscope, perhaps an LCR meter for being able to measure things like inductance, and then some kind of rotary encoder so that we can measure omega m. Okay, and more on this in a little bit. Also, we may want to use a power supply. Well, we will need to use a power supply for sure to power our motor. Objective 2 is we want to use, or I'm going to require that we use a lossless, in other words, no friction encoder, such as a Hall effect sensor with a magnet disc that would be mounted on the rotary shaft. So there's different ways of, lots of different encoders. There's optical encoders, but I'm going to propose a Hall effect encoder. Those of you who are actually going to run these experiments, this is what I have available for you to use, and they're pretty easy to use. This leads to a third requirement, which is to require only steady state omega m measurements. This is what's easiest when using a Hall effect sensor or an optical sensor and a digital multimeter or a DSO. Essentially, an encoder, or these types of encoders, produce pulses. The number of pulses that they produce per revolution is going to depend on the specifics of the encoder in your setup, but there will be a fixed number of pulses per revolution, and so if you can count the pulses or count the frequency of the pulses, you can calculate the actual RPM, revolutions per minute, or radians per second of the motor shaft. So to make this measurement, you need to actually have some kind of equipment that is able to measure the period between pulses. So if I have a pulse like this initially, and then later on we have pulses that are much closer together, then this tells us that omega m here is greater than omega 2 is greater than omega m1, where this would be this would lead to omega m1. So the first set of pulses is the case where we're rotating at an omega m1. Second set of pulses, we're rotating at omega m2. It's clearly spinning faster, and we have to use a DSO or a multimeter to actually measure this frequency. So if you want to measure how omega m changes in time, then you would have to capture a long pulse train of these pulses coming from your encoder, capture them, say, on a DSO, and if it takes, say, 2 seconds for your motor to spin up, you're going to have to capture that pulse train for a whole 2 seconds, and then you'll have to zoom in to every, down to the level where you can distinguish one period from another, and then let the DSO measure the period or the frequency, and then you'll have to pan through that entire capture. So for that reason, we're going to require simply the steady state angular frequency measurements, or that's our goal, because in that case we don't have to capture a long pulse train. We just let the motor run to steady state, display the pulsed output of our encoder on the DSO or on the DMM and turn on a frequency or period measurement and record that value for each condition under which we want to measure a steady state response of our motor. Fourth, we would like to run all of our tests without having to load the motor. In other words, tau load is going to be equal to 0. There are tests you can run where you would load the motor, and that's appropriate to do. That takes a lot more setup and calibration, and we want this to be as simple as possible. So initially we're going to devise experiments that don't require any loading, so it's a free running motor. And then lastly, we want to complete all tests without damaging the motor, so that we're not going to tear it apart, we're not going to run it to some point of failure, etc. Okay, so up to this point we have developed a block diagram model of our motor in addition to the schematic representation. We've also assumed some under steady state conditions. Let's see, our steady state conditions were back here, where under steady state conditions we claim that d omega m dt is equal to 0, and therefore tau jm is equal to 0, leaving all of the induced torque, tau I, that's produced from the electrical side of the motor, being distributed to the viscous loss and the stiction loss. And if we had a load, but the load we're going to assume is 0, as we have set as an objective. So we considered this case of steady state and worked through that to the point where we arrived at some expression for omega m. I've subsequently cleaned that up into a more tidy package. So steady state omega m, and we look at this expression, we note that the steady state angular frequency is a function of our external motor voltage. It's a function of our motor constant. It's a function of the armature resistance. It's a function of the viscous loss coefficient of our motor, and it's a function of the stiction loss of our motor, and we're going to assume tau load is 0. So if we knew, let's see, there's 1, 2, 3, 4, 5, there are 5 parameters there. If we knew any 4 of those parameters, then we could calculate the 5th one. But the problem is, as we start out trying to extract these parameters, we don't know any of these. Well, we know omega m, or I'm sorry, Vm, because we're going to specify an external applied voltage, but we don't know Km, we don't know Ra, we don't know Bm, we don't know tau s. So we can't simply use these results to come up with a progressive set of experiments that will lead to determination of all 6 motor parameters. We need to get smarter about this, and to do this we're going to go back to our circuit representation. And there are a couple parameters here that are readily determinable or measurable. And I think this will be quite obvious to anyone who's worked in an electronics lab, and that is that your parameters, the parameters of LA and RA, can be measured with standard laboratory electronic equipment. Now the trick for measuring this is that we need to make sure when we connect to the terminals of our motor, recall that this is in a box, right? We cannot access any of this internally. So the only thing we have access to is we can set Vm, we can measure Ia, that's easy to do, and then we're going to measure omega m over here. So assume that we can observe these 3 things. Now let's look at these parameters that are to be extracted. Well, first consider Ra and La. If we can force Ea to equal to 0, then Ra and La can be measured much as a discrete inductor or resistor might be measured. So the question is, how does one force Ea to be equal to 0? A caution: the position of the rotor may affect your RA measurement, since theta M impacts the brush commutator contact point. You want to be sure that the brushes are making good contact with only one coil. Here's a tip. When measuring RA, you might also consider the advantages of using a current-controlled power supply along with the multimeter. Tip 2. Measuring LA requires choosing a test frequency. If you use too high of a frequency, the inductance of the motor coil will begin to look capacitive, and this will mask a good inductance measurement. Too low of a frequency will result in a poor measurement as well, if Z of LA is much less than that of the resistor RA. So now let's assume that we have determined RA and LA. So going forward, we can use RA to help determine the other parameters. Let's consider LA further. If our tests are steady-state tests, then dIA dt will be 0 since the current won't be changing in time. And d omega m dt will also be 0 because the motor shaft will not be changing in time. It will be at a fixed frequency. So therefore LA and Jm vanish. In other words, they don't show themselves during these steady-state tests. Note that even when d omega m dt is not equal to 0, in other words, the shaft is accelerating or decelerating, we can still ignore LA in most cases because the time constant associated with LA and RA, that is, LA over RA, will be much, much less than the mechanical time constants of the system. So, given RA and LA, what should we extract next? And assume we have RA, we know LA, but we're going to be able to ignore that. And we are looking to identify Km, tau S, and Bm. We're assuming tau load is equal to 0. So of these three, which should we pursue first? Km is central to the coupling between the electrical and mechanical portions of the system. So let's try to determine Km. So note, the induced voltage, armature voltage EA, is equal to Km times omega m. If we could measure omega m and we could measure EA, then we could determine Km. The problem is we can't measure EA. We can't directly measure EA. However, we note from KVL, and referring to the circuit diagram above, that EA can be determined by knowing VM, knowing the current IA flowing in, and knowing RA. So VM can be set, and we can control this. This is external. We can set it. We can measure it. RA, we have already measured. We've already determined. And IA, we can measure. That's an external current that's coming in, and we're going to assume that we have a means to be able to measure current. Particularly if it's a steady-state current, then we can use something like a multimeter. If it's a transient current, then we need to consider adding in a resistor and measuring the voltage with the DSO, or we need to have a more sophisticated current probe for our DSO, which we have not listed among our assets. So we conclude that there is, in fact, a way to determine Km given RA and measured values of VM, IA, and omega m. So we now have RA, LA, and Km. This leaves the viscous coefficient Bm and the viscous or the static or stiction torque loss tau S. And of course there's Jm, but this cannot be determined from steady-state measurements, so this will have to be considered separately. Let's go back to our motor schematic, and talk through this one. All right, our diagram shows what we can measure or have already determined. We can measure VM, IA, we know RA, we now know Km, and we can also measure omega m. So it seems hopeful that we should be able to get Bm and tau S. So let's look at the force equation, or the torque equilibrium equation on the right side. Okay, so if we sum the torques to 0, we have tau I minus tau s is the net torque, we'll say, that is being applied to Jm, Bm, and tau load. But in this case, because we're in steady state, there is no tau of Jm and we have no external load. So the only opposing torque we have is tau Bm. In fact, I will rewrite this as tau I equal to tau s plus tau Bm. And we can rewrite this again as tau s plus Bm times omega m. Now we know we can measure omega m. We don't know tau s. We don't know Bm. But do we know tau I? Tau I is Km times Ia. Do we know Km? We do. And can we measure Ia? Yes, we can. So what we really have here is we have some equation that's of the form y is equal to mx plus b. The x in this case is omega m. As long as we can take measurements at multiple points on this plot, on this line, then we can determine m, which is Bm ultimately, and b, which is our tau s. Now the challenge here is that you can't directly set omega m. We don't have like an omega m energy source. You know, what do we get to change? We get to change Vm, right? Or we get to change the current that we apply to the motor. So you could actually power the motor with a current controlled power supply, and thereby you'd set Ia directly, which would be indirectly, effectively setting tau I. And you can try that. But there are some practical limitations or implications of what is more readily achievable in the lab. For instance, if when you apply a voltage to the motor and you vary the voltage on the motor, say from 0.5 volts up to 3.5 volts, you can imagine that the speed of the motor is going to change significantly over that time. But do you know how much the current will change over that span of voltages? If the motor is unloaded, the current may, but it may not actually change current significantly. If the current changes very little over that range of voltage, then if you're going to set up a test where you're going to program a fixed current, Ia, that's going to be pushed into your motor, it will be your motor speed and operating point will be very sensitive to the current that you apply, because after all, over this span of input voltages and RPMs of the motor, the current changes very little. In such a case, it would be preferable to actually apply a voltage, set the voltage Vm, and then measure the current. As long as you can change the voltage, and ultimately that changes the current, or you can change the voltage and that ultimately changes omega m, then you've achieved the objective, which is to plot this y equals mx plus b line for multiple points, and sufficiently so that you can then use some kind of number fitting or curve fitting to be able to extract the slope m and the y-intercept b. So I think I'll leave it at this, and after you've successfully completed this part of the experiment, you will have in hand the following parameters: Ra, La, Km, Bm, and tau s. All that is left to determine is Jm, and this will require a transient experiment, not a steady state one. So we have to go back and think about something that we're going to capture in time that will show how the motor spins up or how the motor spins down. And we're going to have to do that with the caveat that that we stated at the beginning, which was, or we're going to require that we only take steady state omega m measurements. So this is going to be a challenge, because if we're going to be watching the motor spin up or spin down, then how do we actually determine, or how can we observe the angular frequency of the motor without directly measuring omega m? Not that we can't measure it, we can measure it, but only in steady state. And here we're going to have to measure an omega m that changes in time. And I will give you a hint to this, okay? If we look at our model, in this case we note that EA is equal to Km omega m. Now if we want to measure omega m, we could measure omega m indirectly if we could measure EA and we knew Km. Well, fortunately we know Km, but can we measure EA directly? We can't, not directly at least. But can we measure EA indirectly? Well, we note that EA is equal to, again by KVL, Vm minus Ra times Ia. Do we know Vm? We do. Do we know Ra? We do. And can we measure Ia? Yes, we can. So we can ultimately measure EA kind of indirectly, okay? Indirectly by knowing Vm, Ra, and Ia. Now, another important hint to finding Jm is we note that Jm, this is from Newton's second law, just like we have F is equal to ma, or md velocity dt, we have torque is equal to Jm times d alpha, or we'll write it as Jm times alpha, or Jm times d omega m dt. Okay, so we can find Jm if we know the torque and we know d omega m dt. Note, we only need to know the change in omega m. We don't need to know omega m directly. So therefore, if you're trying to measure omega m, going back to this equation here, what we're only looking for is we're looking for d omega m dt, which can be found as dEA dt divided by Km. And dEA dt can be further expanded into dVm dt minus Ra dia dt. So you need to think of a test where that test will result in the physical motor undergoing a d omega m dt. And recall that in order to calculate Jm, you're going to need not only the time rate of change of omega m, but also the torque that is applied to tau Jm. You'll be able to determine d omega m dt indirectly if you can determine dEA dt. And dEA dt being made up of two components, you should consider if your experiment can fix one of those to not change in time, then you're really only talking about determining the time rate of change of one of those parameters. So let's say that you fix Vm, then you're going to look for a time rate of change of Ia. If you were to fix Ia, then you would look only for a time rate of change of Vm. Now lastly, how do you measure the torque that is applied to Jm? We can't measure the torque directly. However, we know that tau I is equal to Km times Ia, and we can measure Ia and we know Km. So we can indirectly know what tau I is. Now tau I is going to be divided between our stiction loss and our viscous loss and our inertial torque, which will be Jm d omega m dt. So indirectly, we can measure tau I. And indirectly, we're going to say that we can measure d omega m dt by what we've discussed previously. Now, you will know tau s at this point, because this is the last parameter you're going to be extracting. You will also know Bm. So theoretically, if you know omega m and you know d omega m dt, then you could, from this expression here, you could find Jm. But up to this point, we said that we did not want to measure omega m. It's a transient signal. We can find it indirectly, We did say that. We can find it indirectly by indirectly determining EA, but I think it's an objective to not require this, prefer not to. Okay, so how can you justify away knowing some parameter that's in your equation? Right? To do that, you have to consider the order of magnitude of all the other components in that equation and argue that this particular component in your equation that you'd rather ignore is in fact much, much smaller, or much smaller than the other components, at least under the conditions that you're making this measurement, so that you can avoid having to determine it. And that is one option that you have here. You could decide to make this measurement at an operating point where omega m is going to be small enough such that bm omega m is dwarfed by the other terms in your equation. Now, we don't know yet if tau s is going to be small relative to bm omega m, but if it turns out that Jm d omega m dt ends up being much, much greater than both the losses, tau s and bm omega m, then you could, in principle, even ignore tau s if you wanted to. So setting up the test conditions where you can actually plug in values for this equation and ultimately extract Jm can be thought to be carried out either when the motor is being spun up or when the motor is being spun down. There are two different approaches that you could consider. I'm not saying that both of them will work or that either one or the other is better, but you should consider both cases. How would you spin up a motor? How would you spin down a motor? Clearly, if you spin down the motor, you have to have current flowing here, right? We have assumed there's going to be some kind of torque that is going to be applied to the system, to the rotational inertia, to slow it down. And it's a torque that you need to be able to observe. So if you do spin it down, there are test conditions that you can set up where you can readily determine or measure, observe the actual torque that is being applied to the rotational inertia portion of the system, at least to be able to get a very good estimate of that. All right, I will stop here, and in a subsequent video, then we'll actually present the exact experiments that you can run. But if you are doing this for the Principles of Engineering class, then you should take this information that's been presented here, and then your assignment is to produce the experiments, the specific experiments necessary for extracting these 6 parameters, and only view the next video after you have completed that assignment.